This is a video addressing how to use the TI-36X Pro to solve an integrated rate law problem. So let's first talk about our integrated rate law. There are three different forms of the integrated rate law. The first is the zero order integrated rate law, which says that the concentration of our analyte at time t is equal to negative KT plus the concentration of A at time 0. Our first order integrated rate law says that the ln of the concentration of A at time t is equal to the negative KT plus the natural log of the concentration of A at time 0. And then our second order integrated rate law says that 1 over our concentration of our analyte at time t is equal to KT plus 1 over the concentration of A at time 0. All right, so these are our three different integrated rate laws, and we're going to be using our TI-36X Pro to solve this problem. Okay, you'll note that in all three of these integrated rate law, our x values, which we're going to put in L1, are t. So that is the independent variable, and the dependent variable are these guys right here. Our y for a zero order is equal to the concentration of A at time t. For first order, it's equal to the natural log of the concentration of A at time t. And for second order, we have 1 over the concentration at time t. So we're going to use something called the R square valued that comes out of our linear regression fits in our TI-36X Pro to determine, is this a first order, second order, or zero order rate law. All right, so the first thing that we're going to do is we are going to pull up our data table, and to do that we're going to hit data, and then we're going to plug in our numbers. We're going to type in 165, 604, 1246, 2180, and 6210. All right, those are our x values, our times. Our y values, we're going to do zero order first. Zero order has 0.016, and then 0.015, 0.013, 0.011, and finally 0.0068. Okay, so we've got these values in, and we are going to look at zero order first. So for zero order, we're going to go in and we're going to hit our second function button and our data button, and that brings up this menu. We want to fit this to a straight line, so linear regression, A, x plus b. A is our slope, b is our intercept. We're going to go in. Our x data is in L1, our y data is in L2, and we're going to come down here and we're going to calculate. Okay, and so we get 1.461 times 10 to the negative 6th. That is our A value. That would be our rate constant. Our B value, our intercept, is 0.0154, and that actually is equal to the concentration that we started off with at time 0. And then the most important piece that we're going to look at today is that R squared value, and that R squared value tells us about goodness of fit. the closer it is to 1. A perfect fit is a 1.000. And that 1 is the highest number you can have. So this zero order fits at 0.944. So we're going to look at a circumstance where we have zero order, and then we're going to do the calculation for first order, and then we're going to do the calculation for second order. And we are going to look at that r squared value to determine, is this a first order, a second order, or a zero order integrated rate law. Okay, so we've done zero order. We're going to move on to first order. Okay, to do that, we're going to go back to our data table, and we're going to come over to column 3. Now you could type this in manually, and you could say, for first order, remember we're plotting the natural log of those concentrations, so you could go natural log of 0.016, and then natural log of 0.015, but there's a way to do all of these calculations at once. And to do that, you hit the data button, and you're going to go over and select formula, and we're going to edit the formula in column 3. And for column 3, we want to take the natural log of column 2, and to get column 2, you hit that data button one more time, and we're going to choose L2 and those parentheses, hit enter, and it will populate all of those values in that third column. Okay, so now we're going to go and we're going to do the linear regression for this guy, and to do that you hit your second function button and your data button, and you're going to come down to linear regression, which is number 4, ax plus b, slope is a, intercept is b. Now our y data is now in L3. I'm going to save that L2 data so we can go ahead and do the second order as well without having to retype a bunch of numbers. So you select L3, x data, the time data is still in L1, and our natural log of our concentration is now in L3, and we're going to go down and we're going to calculate. And we're going to find that our slope is equal to negative 1.398 times 10 to the negative 1/234. B is equal to negative 4.145, and our r squared value in this case is equal to 0.986. Okay, so this is a better fit than that, but still not great. We really like to see 0.99 in those first two digits, and 0.999 is going to be what we're really probably after with this set of data. Okay, so that is evaluating first order. That means that this guy would be our rate constant, and this guy is the intercept, and the intercept for a first order reaction is the natural log of that concentration at time 0. So you could back out the original concentration from there. Okay, let's go on to second order. So we're going to go back to our data, and we're going to go over to column 3, and we want to do different math in this column. So we're going to hit data here, we're going to go to formula, we're going to edit that formula on column 3, and we're going to do 1 divided by L2, and to get L2, remember you hit that data button and you come down to L2 and you hit enter, and it has repopulated all of those numbers. And so we're going to go in and we're going to fit that with a straight line. So second data, scroll down to number 4, or you can also type the number 4 and it will select it. Our X data is still in L1. Our Y data is now in L3, and remember that Y data now is 1 over our concentration at the particular time. So we're going to come down and we're going to calculate that. And for our second order, we get A being equal to 0.01413. B is equal to 59.39. And our r squared is equal to 0.999. okay? So that tells us that this order is second order, okay? So we've got a second order rate law that tells us about how this chemistry is going forward, okay? So we are going to determine the form of the rate law. So our rate is going to be equal to our rate constant K times the concentration of C4H6, and all that work that we just did tells us that that is a 2. It's second order. And we also know that K is equal to the slope of that best fit line, which is this number right here. So in this case, K is equal to 0.01413. Now that K does have units on it, and we'll talk about this in class, but often they get left out because they are not always the same. They're reflective of this order right here, okay? So that is the rate law. The integrated rate law would be 1 over our concentration of C4H6 at time t is equal to K times our time in seconds plus R 1 over our concentration of C4H6 at time 0, okay? So that is the form of the rate law. We've gotten the integrated rate law. The value for the rate constant is this guy right here, and our last piece is to determine the concentration at 200 minutes. So we're going to leverage this equation, and we're going to say 1 over our concentration of our stuff at the given time. So that's going to be 200 times 60. We've got our units in seconds here, so we have to have our units in seconds down here. So this is what we're after, is going to be equal to our K value, which is 0.01413, times our time, which in this case is 200 times 60, plus our y-intercept. And that y-intercept is this value right here, so 59.39. So we're going to go ahead and multiply and add these guys together, and we're going to get 1 over x is equal to 0.01413 times 200 times 60 plus 59.39. That gives us 229.07. We're going to take the inverse of that, and we get x to be equal to 0.0043. Okay, and that's the time at, so 200 times 60 gives us a value of 12,000 seconds, which is a little less than double here, and we have a value that is less than this value, so that makes sense. Okay, I hope this helps, and I look forward to seeing you in class.